Good afternoon and welcome to Calculus in the PM. I'm your host, Mr. Sindelka. We're recording live, and if you're watching this, you're not live. 3.4, velocity and other rates of change. Now there's a couple things. Do you guys remember before, this is instantaneous rate of change, but what's the average rate of change? What's the word you'd use in grade 10 for average rate of change? It's a slope, basically, right? Take 2 points, y, change in y over change in x. That's average rate of change. Instantaneous, then, instantaneous rate of change of a function f with respect to x is the derivative. This is at a particular point A. So, that would be like a number like 3. Hey, we've seen this. It's the derivative. Okay. But we know we don't actually have to use that limit, right? We've got shortcuts. We've got ways to do it, provided that limit exists, though. Let's see this. The rate of change of the area of a circle with respect to its radius r. What are we even describing here? Can you imagine? Now, first of all, before we try to do this, if you threw a rock into Wascana Lake or a puddle or whatever, what are you going to see? The first second, boom, you've got that, just where it hit. What do you see like a tenth of a second later? A ripple, and it grows, and then it grows again, and it goes out, right? Now, think about this problem in this context. Find the rate of change of the area of the circle. So the area is the whole thing, right? With respect to its radius, as the radius changes. So, doesn't it make sense that at the start, when you've got a tiny radius, like right in here, and the radius grows just a little onion skin wider, the area has grown a little bit, right? Do you think that's going to be the same rate here then when you just grow a little bit bigger? It's hard to draw. Just a little bit bigger there? Nope. The area will be changing, but you'd think as you get a larger and larger ring, a little bit of radius change will have a bigger effect, right? Okay. So, do we have a formula for the area of a circle that involves radius? I hope you guys know it. We do. Pi r squared, right? But usually, let's just go a of r. You usually just say a. But I want to just remind us, it's a function of radius. That's all that means. It's just the notation we're used to seeing. If you wanted to just put a, that's fine. But with respect to its radius, pi is a constant, we're all agreeing. Radius is changing every second on a on this kind of ripple in the lake, the stone example. So what's the derivative of this? Because pi is just a number. It's 3.14159, etc., right? 2 pi r, okay. So the derivative is 2 times the number, so 2 pi, and then the radius. Hey. By the way, you could have said, and I'll just put this in there, just so you're familiar with notation, dA, the change in area with respect to the radius, dr. It's the same thing if you want to use that notation, right? Okay, anywho, 2 pi r. Hey, do you recognize that formula, by the way? Hey, that's that little onion skin. That's how it's growing, though, right? The area, okay, as the radius grows bigger, you're just growing that little onion skin of circumference. That's how much is added to the area. Okay, that gives you that rate. Rates are speeds. But we always think of speed as per hour, per minute, per second. You can have it. What would the unit be here? Because this is a speed here. And we're talking about the change in, and this is why I like this notation better, the change in area over the change in radius. So what's area's unit? Could be, give me an example. We didn't say this is in centimeters or whatever, but let's use centimeters. So what's the area's unit? Yeah, centimeters squared per unit of radius per centimeter. I know it simplifies to just plain old centimeter, but if you ask me, this makes more sense because it's with respect to how the radius is changing, right? The change in area is whatever that comes out to be. If you put in 1 or whatever, 6.28 centimeters squared every centimeter of radius you increase. That's what that would be. Okay? And yes, you can simplify. So then the next thing is evaluate the rate of change at r equals 5 and r equals 10. Include units, hey. Centimeters, we just talked about it. So, how do we do this? We got the main work, the calculus work is done. This is now arithmetic. What do we do? Come on, don't be shy, give it a try. Tell me. Oh, hey! Don't make me shake my fist. Tell us. Okay, Tristan, tell us. Evaluate the rate of change of the area. Do we have a formula for the rate of change of the area? Yeah, this one. At 5. Radius equals 5. Where? You replace anywhere you see the letter R with 5. I know, it's new to you. That's why I'm showing it as an example. If I thought you could just figure it out, some people could. 2 pi 5. Now, this one I'm showing directly from the formula. The next one we'll just jump in. What would we simplify this to, though? Traditionally, don't multiply out the pi, keep it as pi, but 10 pi, right? So, 10 pi. Now, I'm going to say centimeters squared per centimeter. We could just call it centimeter, but I just want to make sense of the units. Centimeters squared of area per, and that's why I'm putting this out. I wouldn't normally say of area per centimeter of radius. So when you have a 5 centimeter, so it'd be 10 in diameter, circle like I'm holding up with my hands, at that moment the area is growing at a rate of 10 pi units of area. That's what that's telling you. So then at 10, A prime 10. I think you could see and jump straight to the answer 10 times 2, right? We're using this formula again. So 20 pi, and then we'll just say centimeters squared per centimeter. It is not wrong to just say centimeters, but it really doesn't make a lot of sense to do that. It has more meaning, I guess, if you ask me. Now that's one example of a rate. We're going to stick mostly to times, like distances and times and stuff like that, rates. But you could do rates on anything, pretty much. How many exams are written per hour and stuff like this, or, or questions per minute, marks, kids flunking calculus per hour. Motion along a line. So we're here. Let's read it up. If an object is moving along the an axis, we may know its position S, and we use S here, I mentioned this before, instead of D like you do in physics, because if you do dd by dt, it looks stupid, right? Like double D. Whereas ds by dt or S prime, S is not usually used in physics, but we're going to use S here. I don't know why S, but whatever. S is not speed. Okay, we're going to use that as a function of time. So this is what you're going to see here. This is sort of the position function. And yeah, I mentioned we use x more often in physics if you're doing calculus-based physics, x-axis. Definition of instantaneous velocity. The velocity at an instant, right, is the derivative of that s function. Sure, it's defined with a limit, but every time you're doing a derivative, you guys realize you're actually doing a shortcut for a limit. Keep that in mind. Definition of speed, then. How is speed different than velocity? Have you guys talked about that in physics? Yeah.
Velocity is relative to something.
So speed, relative to something.
Velocity is a vector.
Yeah, and what does vector imply? He's right, there. Direction. And the simplest example is, this is a 40 zone right outside the window, right? Let's assume everybody's traveling 40, but there's a big difference between 40 traveling to the west, 40 traveling to the east, right? Direction. And traditionally, you'll choose one direction to be positive. So say east is positive, 40 kilometers per hour. Then the other direction would be negative 40 kilometers per hour. They have different velocities, negative 40 and positive 40, west and east. But would you agree that they have the same absolute value? 40 kilometers per hour is the absolute value. It doesn't, regardless of direction. That's what we mean by the speed. So we're going to use that word carefully here and when you take physics. Who's all in physics right now, this semester, again? Just two of you? Okay. And you guys have talked about that, right? Okay. Everyone else hasn't, they'll probably do it next semester? It'll be good though. Your next semester? Oh, you're not. Okay. So, speed is the absolute value of velocity. The direction is lost. Okay? Positive or negative direction is not important in that case. So, on your calculator, you know how you can do calculations sometimes? If you use that absolute value button, then put inside it your derivative. You know, you can enter this as a derivative dx by dt at t equals, well, I guess you guys have to use dx, dy by dx. But anyways, and x equals 6.2 seconds or whatever. You'll come up with the absolute value of those things. Not that that's tricky, but sometimes it's important. Then acceleration, because not everybody's in physics. I won't assume you guys know these things. Acceleration is how fast you're speeding up, really, the rate of speeding up. Acceleration is the derivative of velocity with respect to time. If a body's velocity is vt, then, and vt is ds by dt, then the body's acceleration at time t is acceleration. The derivative, didn't mean for that, the derivative of the velocity over dv by dt. Or the second derivative, and I mentioned this when we talked about higher order derivatives, the second derivative of your position function. Now when you hear the word position, that's a very carefully chosen word, but commonly you'll say distance, okay? Displacement is a different thing too. Displacement, what is displacement, guys? It's different than distance and position. Just so that we can get the whole idea of position in case you're not sure. I could say my position here is 0. This is my position. And then I have this object and it scoots along here, and I say this is 2 meters. That's its position, right? Okay? Then I'll go backwards a bit. So I should just draw this here. Then it goes backwards a bit. And its new position is 1 meter. Does this make sense? And then this is all in a straight line, all right? Back and forth, east and west. Then I end up at 3 meters. 3 meters is my position. What is my displacement here, if somebody who knows physics? Or if you don't, if you understand the word displacement. Jesse? It's 3. It's the actual movement. Now, displacement and position are often the same. If you start at 0, it is. If I started at 10 meters, if I made this like a 10 here, and this is 11, and this is 12 and 13, my position would be 13 meters, but my displacement would still be 3 meters, right? Okay, you've only moved 3 meters from where you started. So in this case, displacement is how much you've moved. And it is, and it's, I'm going to put +3 just to mean whatever I called my positive direction, whether it's west or east or north or south. 3 meters. It's a coincidence that they're the same as the position. That's what the green's all about. So then the last thing is, what is the total distance traveled without regard to direction? Because distance is a loosey-goosey word, right? But I'm trying to say, well, it would be the 2 meters plus the other meter, so 3 meters plus these 2 meters, so 5 meters. Does that make sense? That's what your odometer measures. You know, the wheeler thing on the car? 5 meters travel, neither positive nor negative. Dig it? Okay. Just so that we understand the words a little better as you come across them. Now, you're not going to have to memorize this. This would be given in any problem, but acceleration due to gravity, free fall constant. English units, imperial system, what they use in the States. Gravity's acceleration is 32 feet per second squared. So that equation becomes, as long as you're starting at 0 speed, you're just dropping an object. Yeah. If you need it, you'll be given this. Metric, and this is what you'd use in physics. Do you guys use 9.80 or 9.81? Yeah. Okay. Some books use 9.8. Anyways. So that's the equation that you'd use. But the acceleration due to gravity here, and you'll be given that. Don't ever try to memorize it. But during these problems, you might just flip back a page or two and refer to that. That's all. So far, we haven't really done much. We've read a lot of things. So let's try something here. And we'll see. Reading a distance graph. Now, it's a distance time graph. Those of you in physics, when you take the slope out on a distance time graph, what do you got? Velocity. Distance, yeah, we could say speed. It depends if the direction is given. Velocity or speed, depending. That's what the slope is. And here, when we take slope, as soon as we hear slope with tangent lines and stuff, we're thinking derivatives, right? I hope so. So, can you see here, this is distance, starting at 0 distance, and it's starting off pretty slow, right? It doesn't cover a lot of distance in a unit time. Then it picks things up pretty fast, right? Because you're thinking tangent line. The tangent line right here is close to 0, isn't it? Then things have picked it up here. Drew a poor tangent line, but you can see it's steeper, right? What's happening here at the top of the hill? Slows down a bit, less steep. What happens right there in the middle? Velocity of 0, right? And you see why? Anytime you see a max or a min on a function that represents position or distance, think 0 speed, 0 velocity. Then it starts speeding up, but in the opposite direction. So it's like me. If I'm standing at this side of the room, I start out really slow, and then I start walking, and then I slow right down, and then I come back, and then I slow down for the last step or two. Oh, I went too far. But anyways, you guys see I don't go right back to the 0 spot, but I go backwards, right? Okay. So that's this graph. I hope you understand this. Accelerating, speeding up. Okay. Accelerating is 0. This is constant speed for this portion. No change in speed. It seems to be pretty constant. There's a change in speed. We have a value for acceleration. Right? You're braking. Negative acceleration. Don't say decelerate. Mallet tells you that too, right? Does he ever tell you not to say decelerate, or did you? Okay. Now, reading a velocity graph is trickier. And those of you in physics have seen these before, right? And it is trickier. It's a little more abstract. You guys know how to go from a velocity graph to a distance or change in position? What do you do? No? I thought you were the smartest. No? Okay. You guys don't, maybe you guys didn't talk about it. You guys ever find the area under a graph? Okay, that's how you go, don't worry, physics. We will use a calculus method to do area, but that's not for a couple months. Don't worry. Okay, a particle moves along its x-axis. Its velocity is shown in the graph below. Describe the motion and state when the speed is at a maximum. Okay, right here at the start, is it moving? No, it's just stand still. I don't know if you need to do that. What's happening between here and here? It's accelerating, speeding up. Good. You might want to label that then, if you want. Accelerating. Speeds up. Maybe I don't want to. Accelerates. And I'm going to put positive, meaning speeding up kind of acceleration, because negative acceleration in the positive direction. We'll talk about those things. What's happening right here? Are you moving here?
Yeah.
Yep. What? Tell me. At a constant speed. It's not changing. Constant speed there. The acceleration is 0. Okay? Constant speed. I'll put this here. Acceleration equals 0. By the way, you don't have to use my typewriter A. You can use a regular A. Something I tend to do, that's all. What's happening here? Negative acceleration. Okay. Negative acceleration. In this case, it's slowing down, right? Okay. Is the 0 important? Is it? When v equals 0, what does that mean? It's not moving. Stopped momentarily, but it is stopped, right? So v equals 0. I'll just put stopped. As long as, sometimes people get problems and they say, you didn't give me one of the speeds, and I need it. It says here, starts at a standstill. Oh, yeah, 0. Then what happens? What kind of acceleration is this, or is it acceleration? Well, I guess on the curvy part, kind of drops. Yeah, it is, eh? What is it? Negative acceleration. Does that mean it's speeding up or slowing down, though? Negative acceleration means speeding up. It's true. Well, what do you mean by that? How? Give me an example. Okay, if I throw this eraser up in the air, right? It leaves my hand with its fastest possible speed. Maybe it's, and it doesn't have any meters per second. Okay, let's say I can somehow give it 1.8 meters per second out of my hand. That's not far-fetched, eh? Okay, and as soon as it leaves my hand, it's going to slow down to 0 at the top, and then come back down, and then fall, there, and it speeds up on its way down. Now, this, if it was a rubber ball, would hit the ground and then bounce up maybe 2, So, do you guys understand what that's meaning? This is sort of like, I guess you could say, a ball right here. This is a ball going up and then hits 0 speed. Then from here to here, slows down, goes the opposite direction, speeds up, but going in the opposite direction, negative speeds. That just means, all these negative speeds just means going west instead of east or something like that, right? Comes to a stop again, and then speeds up. Okay, you guys getting it from here? Okay, I'm not going to beat this one up too much. Yep, all yours. Where? Oh, right, sorry. You're right, it doesn't stop. Thank you. It only stops when it's right here. It doesn't stop. It reaches its max velocity or in the negative direction. Thank you so much. I said bad stuff. He's right. Doesn't stop. It doesn't even stay constant there. I'll say minimum velocity because it's actually a negative direction, right? Bad advice from Shindelka. Minimum velocity in this case is your maximum speed. Good thing you pointed that out. And it picks it up. Yeah. Slows down for this portion, hits 0, then it goes in the positive direction again, right? Thank you. I find them counterintuitive, and I even made that mistake, treated it like a distance time graph. If your teacher can't do this, you guys are screwed. Okay, let's try this here. Now, modeling vertical motion, straight up and down, that's vertical, right? Dynamite blast. Propels a heavy rock straight up with a launch velocity of, and this is in feet per second, 160 feet per second. It reaches a height of, we've got a function for this position. Like I said, often you'll be given the function, so you don't have to memorize 9.8 or 16 feet per second squared and stuff. After t seconds. How high does the rock go? Well, this is a position function, right? So how high does the rock go? How do we figure that out? What's the speed of the rock at its highest spot? 0. So you have to find the velocity function. Set it equal to 0. Then you'll have the time. Right? And then you can plug that into the position function. People with who are taking physics right now, that's probably occurred to you right away. You knew what to do, right? You didn't? Okay, well then it's a good thing. I won't assume anything because I won't. I don't usually. So how high does the rock go? Well, we don't know right now, but we do know at max height, speed is equal to 0, right? I throw this pen up in the air, the maximum height, it had to stop and then come back down. Everybody agree with that? Yeah. Okay. At max height, v equals 0. So we need the velocity function. We have the s function, the position function. How do you get the velocity from that? I hear it mumbled a couple times. Somebody say it with conviction. Yeah, the derivative. Okay, and I'm not making it up, it's from here, right? Speed is the derivative of the position function. Incidentally, the second derivative of that is the acceleration function. Often acceleration is a constant. So back to here. At max height, the v is equal to 0. So we know that v is equal to v of t, the function, is equal to s prime. Now, so v of t in this case, velocity is a function. I'm making it look more like math than physics when I put v of t, but that's not a biggie. 160 is 160t minus 2 times 16, so 32t. Y'all agreeing? What do we know about the velocity at the max height? It's 0. We just said that, right? Max height v equals 0. So 0 equals 160 minus 32. I sure hope you can solve that, so I'll solve it for you. You would add the 32 to the other side. 32t equals 160, right? 160 divided by 32. You got me? 5. Now I'm just doing that for space reasons. I would have actually shown the work. Have I solved this? No, this is when it is at its maximum height, right? I want to know how high it actually goes, though. I don't really care about the time other than I need it to solve this. So what do we do now? The position function, right. So we know now max height at t equals 5 seconds. That's what we solved in green. So S of 5, I'll make my 5 look different than the S, is equal to 160 times 5, 16 times 5 squared. And I'll do it in calculator, I did it, 400. You could do this without one, but 400 feet is the max height. I'll accept things like max height. If you're doing an AP thing, they'll write the word maximum. So if you're somebody who wants to develop the habit right now, write out the full word. I'm fine with max. I actually think they are too, but I can't promise you that. Does that make it some sense? That's algebra though. Like there's no calculus done so far, correct? Oh, we did calculus. That's how we got the velocity function. My mistake. Yep. Yeah, we did. Okay. Yeah. I guess I was thinking you could have done this though in physics because you got that V naught minus 18. That's a physics equation. But yeah, we did calculus to get that. What is the velocity and speed? They're asking two things. They're not synonyms, and we've talked about this. One has direction, one doesn't. The velocity of the speed when it's 256 feet above the ground on the way up and on the way down. We need to find the times when it's at 256 feet above the ground, on the way up and on the way down. So, t equals question mark. It's obviously twice, right? When S of t equals. Then we can find the velocity and the speed. So, we got a function for this, right? 160t minus 16t squared. So we know that 256 is the S value. I'm using this, right? So 256. I'm going to drop the units while I solve this. 160t minus 16t squared. Y'all dig that? So it's quadratic. We've got to get everything to the one side. We'll go 16t onto this side squared. If you're a big sissy, you'd use a calculator to solve this, but you guys can factor this. What do you take out first, though? Any common? 16. You guys know this one?
Is it 16?
It's 16 squared. Yeah, 16. Think about it. It's not too bad to factor. 8 and 2, right? And we have more negatives than... Oh, no. Yeah, negative 8, negative 2. Yep. So, 8 seconds and 2 seconds are 2 times. So, what is the velocity and the speed of the rod? We got to use this function, right? Oh, gosh. So V of, we'll go with 2 first. You can do this in your head probably. 160 minus 64 is 64, 96. But you're right. You were thinking it though. And that's positive 96, right? And it should be on the way up, 2 seconds. Positive. And this is in units of meters per second, I think? Or was it feet? It was feet. Second. Okay. And I'll use a different color here. 8. I got to remember to bring some snout rags tomorrow, eh? At 8, you got 8 times 32. So subtracting 8 times 32. But do you know what? $256? It's negative though.
Yeah.
So the difference between 256 and 160 is? Make it negative. 96. Hey, on the way up and on the way down, it's the exact same speed at the same spot. Speed. Velocity is different because it's got different direction, right? So, same speed. If you're not worried about going up or down, it's the same speed. And that is generally the case. Yes.
On the test, can we just show that it's the same? Like, can we just wait, like, once we get 96 feet per second on the way?
Oh, if I asked you for speed and velocity, yeah, you could do that. I think you could. Just say same speed and velocity. Like I did, right? Same speed. Yes. Now, acceleration at any time. So I'm telling you it's the same all the time. If we have a velocity function, we can go, because it's the second derivative of this s function. So take the derivative of the v function. Acceleration at any time is equal to dv by dt. Which in this case is 160 minus 32. It's minus 32. If you're in physics, you might know what the units are. But you know how, I told you before too, the d by dt notation gives you a better idea of what your units are. Think of this as the second derivative of the position function over dt squared, right? Now, it's d squared, but not s. So it's feet, right, per second squared. The calculus, that kind of thing helps you find the units better. If you know a bit about physics, you probably wouldn't even think about feet per second squared, meters per second squared, etc. Kilometers per hour squared if we're talking about different problems and so on. Now, gosh, this doesn't end, does it? When does the rock hit the ground? So when is the position 0? It's obviously at the start, it's 0, but then if we're starting at 0 and then it comes back down, that's when we're finding it, the second 0, right? So 160t, oh, it's right here. I'm looking at it, minus 16 squared, right. Okay, you could solve that one by factoring. Common factor of 16t. Right. 10 minus t. 0. So we expected this one to come up. The initial starting time is 0 or 10 seconds later. That's when it hits the ground. At 10 seconds, I guess I should say, instead of after, but after 10 seconds elapsed, I guess, but we'll be careful. Okay? Now, I think you guys have had enough. So I'm going to pause.